Now let's do our very short course on calculus, because it's good to understand why are we here. So what's our very short course on calculus? Well, we understand flat things well. So what do I mean by a flat thing? Well, these flat things are things such as lines, rectangles, boxes, and a three-dimensional version of course, the line, which is a plane. Now, you might notice that I actually drew a proper plane this time. Usually I drew an airplane, but I'm trying to draw things on the computer, and it turns out it's hard to draw things on a computer, so I just went with a normal plane. All right, so we understand flat things well. The problem is what's around us isn't flat. So you don't see a straight line, you see a wiggle. You don't see a rectangle, you see a blob. And you don't see a box, you see some crazy three-dimensional shape. And instead of a plane, you get some sort of a surface. This is sort of like a bubble here. So how do we resolve these things? How do we say, look, there are things I can do very well, but they're not the things I need to understand. And the way we resolve it is the following. We approximate things which are not flat by things which are flat. So in Calculus 1, basically we said, hey, instead of a wiggly thing, let's put all our attention on lines. Because we can understand lines really well. And then once we got those lines down, we said, fantastic, how do we approximate a wiggly thing? And we found a way to do that. So in fact, let's talk about that, because there are two sides to calculus. So the two halves of calculus, there's what's called differential calculus, and that's asking the following question, what is the rate of change? And there's integral calculus, which is asking what is the total. Now both are important. You need both aspects depending upon what context you're in. And they're also connected to one another. They're connected by what's known as the fundamental theorem of calculus. The fundamental theorem of calculus says that these two topics, finding the total and finding the rate of change, tie together. And basically, it's what does the fundamental theorem say? Well, what is the rate of change of the total? And the answer is, well, whatever object you have. Easy question, easy answer. All right, so let's talk about the idea of differential calculus. Well, I might have some sort of wiggly curve that moves up and down. And I want to say, well, how is it changing? And the answer is, aha, it depends. Because I can see in some places I'm going up, I can see in other places I'm going down. So there's not an answer to how is it changing, just, well, it depends on what you're doing at that particular time. But what I can say is, well, how is it changing right here? At that one spot. I want to know what's happening there. So the way we do is we say, well, let's take out our magnifying glass and let's zoom in a little bit. So we zoom in, and if we zoom in, lo and behold, what we'll see is something that's a little bit more reasonable. So okay, we're losing a little bit of our wiggle, but still wiggling a bit. So I say, no problem. We'll pull out our microscope. We pull out our microscope. And what happens? Well, we zoom in, and lo and behold, it's even less wiggly. It's becoming flatter and flatter. You say, well, look, can we go even further? You say, yeah, no problem. We'll go over to physics. They take all the money from math and invest in expensive machines. We'll use their tools. So, scanning electron microscope. And if you zoom in super, super close, lo and behold, it looks flat. Now, of course, it looks flat. You might say, is it truly flat? Well, no, there's an ever so slight bend. But close enough, close enough. So you say, well, if I want to understand what's happening at this point, really, there's this nice flat thing here, a nice flat line, and I can approximate this behavior locally by a flat line. And lines are easy to understand. That's the mantra. Flat things are easy to understand. So rate of change of a line, what is that? What is it? Do you remember? It's the slope. So lo and behold, I can answer what the rate of change of a line is. So if I can approximate something by a line, this is my approximation, I can answer the question to how it's changing. All right, that's differential calculus. What's integral calculus? Well, integral calculus is a total. And total what? Well, total of anything you need. A lot of people think integral calculus is just about total area. It's not a bad first impression. It's not right, but it's not bad. We oftentimes introduce integration by area, but really it's a finding the total. So for example, if you take a Calc 2 class, you'll talk about various things such as, I should use a darker blue color. You'll talk about various things such as total volume. You'll talk about surface area, length, mass, all these types of things. We're going to do several of these things again this semester. So let's suppose we are talking about area just to help us get started. So I might say, well, what's the total area between A and B? Well, we want to do the following. We want to say, let's approximate by something which we understand. What's something we understand the area for? Yeah, squares or rectangles. So this is, if this had been a rectangle, life would have been great. It's not a rectangle, but life's still great. What we do is we say, well, let's just take this and we'll chop it into little pieces. And we'll say, okay, well, what does that do? Well, every little piece is like a very tall, skinny rectangle. And of course, the problem is it's not a perfect rectangle because there's a little tiny bit of an error. But not much. Very small. And so if I approximate each one of these strips by a rectangle, it's a good approximation to the total. But how can I do better? Yeah, smaller rectangles, better approximation. So in general, there's this idea in calculus that says, look, as you get smaller, approximations get better. It happened in both cases. So in the differential calculus, the getting smaller says zoom in closer, you better approximate the function. In integral calculus, it says break into more pieces, you better approximate the total. And so here we break into small parts and add it up. And we're going to get to do both of these things in our class because we're doing both integration and differentiation. All right. So if we're going to start from the beginning, we need to start with basic geometry. In calculus, it's motivated by geometry. Now, do you know where the word geometry comes from? And I guess I shouldn't say not words, but the word. Geometry, what does it mean?
Shape measuring.
Sorry, what?
Shape measuring.
Shape measuring, that's not a bad. Metry is about measuring. What about the word geo? It means earth. Like, have you ever taken a geography class? It's that same geo. Measuring the earth. So geometry was motivated by an actual application, which was, I want to measure things. I want to say, you know, how far away is that? How tall is that? Maybe there's a very tall tree, and I want to figure out the height. And I don't have a way to climb up it very easily with a ruler or something. Is there a way for me to do this? So there are tools, geometrical tools, that help us answer these types of questions. Now, if we want to understand our geometry, there's two important things. We have to know where we are, which is position, and we have to know how far apart things are, which is distance. So let's talk about position. There's a couple ways to do position. We're going to do the really basic one today. We'll go into some other ones tomorrow. So for position, I can describe where I'm at by talking about distances. So in 2 dimensions, I use a pair of distances. I call them x and y. And I say there's these 2 directions. There's an x direction going one way, a y direction going another way. And so the x says how much do you go in the x direction, and the y says how much do you go in the y direction. And lo and behold, after you follow those 2 steps, you get to a particular point. So here, the x is how much we move, and here the y is how much we move. So what can we say? Well, Hopefully we all know this one. This, by the way, is called the Cartesian coordinate system, named after René Descartes, who, legend has it, was sick one day. And this was back in the day before they had the Xbox. So there wasn't much entertainment. So he was just laying in the bed, looking up at the ceiling, and was watching a fly. This was really top-notch entertainment for his day. And he was saying, how do I figure out where the fly is? And he figured out, well, if I measure the distance from this wall, and I measure the distance from that wall, well, that gives me where the fly is. And thus was born the idea of coordinates. And you might say, wait a second, Descartes, he's kind of modern by comparison to the Greeks. How did the Greeks do coordinates? And the answer is, they didn't. The coordinate system is only a few hundred years old, and the Greeks did geometry without any coordinates. They had it tough. They had it tough. So a couple of things to note. We have the x-axis and the y-axis. The x-axis is when I'm at a point of the form x comma 0. So in other words, it's the points that lie along the x-axis. The y-axis are points of the form 0 comma y. Now, how do we do distance? Well, the distance is the Pythagorean theorem. That's why we spend so much time talking about this theorem. It's really one of the most important theorems in mathematics. So the Pythagorean theorem is about triangles, but not just any kind of triangle. What kind of triangle? The right triangle. Yeah, definitely don't use the wrong triangle. So if you have a right triangle, then what happens here is you have three sides, A, B, and D apparently. And you say A squared plus B squared equals D squared. So in our case, what happens is that the bottom side is how far we've changed in x. It's the magnitude of the change. So it's the absolute value of x2 minus x1. Here, it's the magnitude of the change in the y direction. y2 minus y1. Sorry, it's a little bit faded there, but it does say y2 minus y1. So Pythagorean theorem says if I square this side, so x2 minus x1 squared, and I square that side, y2 minus y1 squared, that's the same as squaring that side, d squared. So now take the square root of both sides. You get d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Two things to note. One thing you might say, hey, you forgot something. I clearly see absolute value signs here that you forgot to carry to the next line. Am I in trouble? Absolute value? No absolute value. Why am I not in trouble? Because I squared it. Yeah. So everything's positive. Life is good. Now, the other thing is you might say, hey, you know, you're making this sound complicated. Because isn't there this like cool idea that if I take the square root of a squared plus b squared, like I'm doing here, doesn't that equal a plus b? No. Now, I am 99.999% confident someone is going to do this on the exam. Possibly someone sitting in this room. They're going to say, I would never make that mistake. I hope that's true. We have to say that square root and addition don't mesh. In fact, they sort of are different creatures. So you have to be very, very careful here. So when in doubt, don't do it. Okay, so that's 2D. So I think we understand two dimensions pretty well. Let's talk about 3D. So in 3D, we're going to have three distances. We have an x direction, a y direction, and a z direction. So we're going to represent this by an axis. Axes here. So the way we're going to draw this throughout the semester is we're going to have an x direction, a y direction, and a z direction. And I should say that when we draw this, that means that the x is increasing coming out, y is increasing going right, z is increasing going up. So if I put the arrows on there, that actually orients things. And mathematics, when we talk about geometry, there's always an orientation built in. Orientation matters. It's going to matter a lot in the last 4 topics of the semester, which are really, really cool because I get to break out my Beyonce songs. But they matter. And so you sometimes will hear this referred to as the right-handed coordinate system. Because there's two options. There's actually two different types of coordinate systems depending upon what you choose. And so we're going to consistently choose this option. This is also, by the way, why you have the right-hand rule. It's a way to break a symmetry. So if, in case you're not familiar, you can just think about standing in the corner. So, for example, just imagine you take yourself and you go stand here in the corner. The z would be pointing straight up. Your right hand, you can think of pointing in the x direction, and your left hand as pointing in the y direction. All right. So, if I'm at a point x, y, z, I have gone there. There's lots of ways to do it. I can move x in the x direction, then I can move y in the y direction, and then I can move z in the z direction. So a couple of notes here. There's a lot of good things to point out. There's a few important axes, and there's also some important planes. So what are the important axes? Well, they're the axes that we have here, the x-axis, the y-axis, and the z-axis. Now, how do I know if I'm on an axis? Well, I'm on an x-axis if my x-coordinate is whatever it wants, but the other two are 0. So that's how I know if I'm on the x-axis. How do I know if I'm on the z-axis? Well, I have 0 for the x-coordinate, 0 for the y-coordinate, and then the z-coordinate can be whatever it wants. Could be 0. That's fine. The origin is in a lot of things. So there will be problems at some point where we'll say, well, make sure you have something which goes through the z-axis. That was a problem from an old exam, which I think is now a quiz problem. So you want to make sure you understand, what does that mean? Well, that means I have a point of the form 0, 0, something. Now, because we're moving up in dimension, we start having other things come into play. So what are some other things we have? Well, we have what are called the planes. Now, there's lots of planes, just as there are lots of lines. But there are three important planes. So there's the floor, which is downstairs here. This is the points of the form x, y, 0. And what do we call it? Well, we call it the xy plane. So the xy plane is where z equals 0. Because the xy plane only involves the x and the y, there's no part of z. So you often will hear reference to the xy plane. That's not the only plane we could have. We could have this plane back here. Well, what do these points look like? They look like 0, y, z. Well, what should we call that plane? Yeah, the yz plane. Because they only involve y and z. And then one last one, which I don't know if this color will show up very well, but what's over here? The xz plane. So one of the things that's useful to understand is if I'm at a point, one thing we might ask is, find the point on the xy plane closest to the point xyz. Well, what's the point on the xy plane closest to xyz? xy0. Just go straight down. That's the closest point, xy0. What if I say, okay, I'm at a point xyz. I want to find the point on the y-axis closest to xyz. What point am I? 0, y0. So if I'm at the point xyz, the closest point on the y-axis is 0, y0. And so forth and so on. It's essentially, if I want to be the closest one on a certain line, a certain axis, or a certain plane, just zero out what you need to zero out. Now that's location. What's the other thing we need to talk about? Distance. Okay, so in 2 dimensions, we did the Pythagorean theorem. What should we do in 3 dimensions? Yeah, what I like to call Pythagorean theorem plus plus. You know, apparently computer scientists do this. You know, they had C, and then they had C plus plus. Okay, well, what does I mean by Pythagorean theorem plus plus? Well, what you can do is you can say, you know, if I'm talking about distance, I'm going from a point x1, y1, z1 to another point x2, y2, z2. And I want to find the distance. Now, when I say distance, what I mean is imagine connecting them by a straight line. what's the length of that straight line? So that's this line here, which is marked D. So I'm interested in what's the length of this line segment. Well, what I can do is I can introduce an auxiliary line segment down here from one corner of this rectangle to another corner, and I'll call that C. Now, if you just stare at this and do a little bit of like cover up, you'll say, wait a second, really this is just a two-dimensional thing because I'm just changing in the x's and the y's. In fact, it's the exact same thing we saw before, where I had x2 minus x1 on one side and y2 minus y1 on another side. And what kind of triangle would I have down here? It's a right triangle. It's not the wrong, it's the right one. Good. On the other hand, I also have another triangle involving C, D, and this segment. And what kind of triangle is that? It's still a right triangle. There's lots of right triangles, and right triangles are very important in our mathematical studies. So, what do? Well, I apply Pythagorean theorem the first time. This length squared, d squared, is that length squared, c squared, plus this side squared. So that's the z2 minus z1 squared. Now, how do I find c squared? Well, Pythagorean theorem. x2 minus x1 squared and y2 minus y1 squared. Okay, so that's my c squared. And so, now I take the square root. Done. Done. Found my distance. Now that we can do distance, we can talk about other things. Let's talk about spheres. Spheres are defined in terms of distances. So when I talk about a sphere, we talk about two things. There's the center of the sphere, and then there's the radius of the sphere. What is the sphere? Well, the sphere is all points which are the distance of the radius away from the center. That's what a sphere is. Now, in particular, let's be careful here. If we were thinking in terms of M&Ms, a sphere is that candy coating. It's not that chocolate which will melt on the inside. No, no. The sphere is just the outer shell. So, given that I define my sphere in terms of distances, it's not unusual to say, hey, I can write the formula for a sphere in terms of distances because one of my points is going to be the center. I'll have that H, K, and L. That's one center point of my sphere. And then I'll say, well, out here on the edge is some point X, Y, and Z. So I can think of, there's a point here, X, Y, Z. And I can say, well, I apply the distance formula. I'll have X minus H squared, Y minus K squared, Z minus L squared is equal to R squared. So the formula for the sphere follows immediately from the formula for distance. Now, the formula for the sphere, again, that's the shell, but maybe we don't want the shell. Maybe we want the inside, or maybe we want the outside. So let's think about it. What's true about the points that are inside the sphere? How far are they away? You might say, that doesn't sound like a very good question. What's true about the distance from a point from HKL to any point inside the sphere?
Inside the radius.
It's less than the radius. That's what this says. I'm on the interior if my distance is less than the radius. Now you might say that's not quite what it says because you squared it to make it look pretty. I did square it to make it look pretty. But that's what it says. Now what if I'm on the outside? What can I say about my distance to the center? It's greater than R. So x minus h squared plus y minus k squared plus z minus l squared is greater than r squared. All right. So I think we have time for an example. I hope so. We should have at least one example a day. One example a day. Okay, so here's our example. Find the center and radius of the following sphere. Now you'll notice I forgot to write down an equation, so let's go ahead and write it down. So I'll need some help from the audience. So x squared plus, give me a number.
6.
6, all right, that's a nice number. X plus y squared plus?
30.
What? Really? Okay. All right. All right. Plus z squared. I'll do a minus this time. 2. Okay. Somebody likes me. All right. Equals 0. Works for me. Okay. So I claim this is a sphere. Now, you might say, I don't think you're right, but that's okay. I'll try to convince you. Now, you might say, well, why might we not think it's a sphere? Well, it doesn't have the form of a sphere. A sphere looks like x minus h squared plus y minus k squared plus z minus l squared. We don't have that. We don't have that. Not yet. All right. Well, let's think about it. So I have x squared plus 6x. And then I have y squared plus 13y. And I have z squared minus 2z. All right. Now, if we think about it, we really want to have something like x minus h squared. Currently, I have x squared plus 6x. So I really want to have a perfect square. Somehow, right now, it's not quite a perfect square. It doesn't yet feel complete. How can I make this into a perfect square? Just, again, only focusing on the x squared plus 6x. What can I do? I could add 9. If I added 9 here, lo and behold, this becomes x plus 3 quantity squared. But I can't just add 9 here. Now, I could subtract 9. That's okay. That balances out. Or I could add 9, as was said, to the other side. All right. Now, what happened? Side note. If I wanted a perfect square, x plus a squared is an example of a perfect square. That's x squared plus 2ax plus a squared. So we said, aha, this 6 was my 2a. So that's why we said, oh, divided by 2, which became 3, and squared. That's where the 9 came from. Okay, how about this z squared minus 2z, which I didn't leave a lot of room for. What would I want to do? I want to add plus 1. So plus 1. Okay, this becomes z minus 1 squared. And how about here? What would I like to add? 169/4, right? Good. Right? Because 13 divided by 2 is 13 divided by 2. So this becomes y plus 13 over 2 squared. And if you square 13 over 2, you get 169/4. Yes, that's what we get. Now, so if we clean this up a little bit, you get x plus 3 quantity squared plus y plus 13 halves quantity squared plus z minus 1 quantity squared equals 9 plus 1 plus 169/4, which we can also write as 209/4. Now, you might say, that seems really fast. 9 plus 1 turned out to be nice. It turned out to be 10. 10 is also 40/4. And 169 plus 40 is 209. Okay. What's my center? -3. -3. Wait, this says +3. Yeah, you remember it's x minus h, right? So it's not x plus 3. It's really x minus -3. So it is a -3, comma, -13/2, comma, 1. What's my radius? Yeah, square root of 209/4. And square root of 209 is not nice. So we'll just leave it like that.